experiment of Kirchhoff laws. In this lab, you will be exploring circuits having resistance in series and parallel combinations. You will even analyze complex circuit with 3 branches and 2 voltage sources using Kirchhoff's rules. The purpose of this experiment to verify Kirchhoff's first and second laws. This apparatus, voltmeter and ammeter and connecting wires. Also, you need power supply. The theory. First Kirchhoff law, the sum of all currents leaving a node in any electrical network is always equal to 0. Sigma I equal I1 plus I2 plus I3 equal 0. Kirchhoff's second law is based upon the law of the conservation of energy. It states that the total voltage across circuit loop is equal to the sum of the voltage drops across the device in that loop. Essentially, the energy you put into the circuit equals the energy you get out of each circuit loop. An equation can be produced for each loop in a circuit. For example, Vin or Vin equal V1 equal V2. Also equal IR1 plus IR2, because V voltage equal current times resistance. Conventions of loop rule. The following conventions apply for determining the sign of delta V across circuit elements. The travel direction is the direction that we choose to proceed around the loop. Here in this table, the first travel direction, high V, lower V, you get out delta V equal VB minus VA equal minus I times R. Another travel direction, here case lower V to higher V. Delta V equal VB minus VA equal plus I times R. In other case, travel direction lower V, higher V. Delta V equal VB minus VA equal plus E. E the power source. Yeah. Same direction V here. E lower V. Delta V VB equal VA minus E, this power supply. Application of Kirchhoff's second law defining outside convection is important. Here direction of loop, sign of E is positive. And here direction of loop, here in R, go to I, sign of V or IR is positive. This example, learning with this example, you have 3 resistance, R1 equal 10 ohm, R2 equal 20 ohm, R3 42 amp. You have two power supplies. The first 10 volt, other 20 volt. You have two nodes, A and B. Step 1, you draw closed loop in the circuit. Define the direction of flow of current in the circuit as seen in the above diagram. Note that the direction does not have to be the actual direction in which the current is following, using Kirchhoff first law. At A, and you can see this is the same example. The circuit has two nodes at A and B. We have the choice of choosing only two on the three loops shown below. This is because only two of the loops are independent. In node A, have I1 plus I2 equal I3. At node B, I3 equal I1 plus I2. Loop 1, 10 voltage equal I1 R1 minus I3 R3 equals 0. Loop 2, 20 minus I2 R2 minus I3 R3 equals 0. Then another step, I1 plus I2 equal I3. Now you can get I3 equal I1 plus I2 at the second. 10 equal I1 R1 minus I3 R3 equals 0. 20 minus I2 R2 minus I3 R3 equals 0. By substitution, the answer can be shown that I1 equal minus 0.143 amperes and 12, and I2 equal 0.429 amperes. This is the same exactly when you are doing your experiment like this example. And now you can see the experiment on this video. Thank you.
Okay guys, so this is the experimental setup we are going to use. This is the breadboard. You know it from Ohm's experiment. And we are using these three resistors. This resistor to the left, 47 ohms, as you can see here written. And the resistance to the right, which is R2, called R2 in the lab report, is 470 ohms. And this is the third resistor, 100 ohms, R3. And from this side, we connected this power supply, the positive terminal up and the negative terminal down, and adjusted to 6 volts. This is arbitrary, so I choose to adjust at 6. This is the second power supply to the left, the positive terminal up and the negative terminal down, and adjusted to 10 volts. Now I will start measuring the voltages and the currents. I will start by measuring the voltage across each resistor using this voltmeter. So I will first measure the potential difference across R1, the 47 ohms. Yes, it says 3.256 volts. 3.25. And the positive terminal is to the left, the negative terminal is to the right, which means the current is flowing to the right in this direction. I will switch now to the second resistance. It says 0.75 volts. 0.75 volts, the positive terminal to the left, the negative terminal to the right, the current is flowing to the left. Now I'll switch to the third resistance. It says 6.799, around 6.8 volts, and the positive terminal is up, the negative terminal is down. These are the three values of the potential differences. Now I'll start measuring. Okay, now I will measure the three currents. I will start by measuring the current in R1. I will shift this to connect the ammeter in series with the resistance. It says 68.05 milliamperes. The positive terminal to the left, the negative terminal to the right. Now I will measure the current in the resistance R2. It says 1.61 milliampere, 1.61 milliampere, and the positive terminal is connected to the left and the negative terminal is connected to the right. Okay, now I will go to the third resistance, R3. Connecting the ammeter in series. It says 66.89 milliamperes. The positive terminal is up, the negative terminal is down. So these are the three values. Now I will write down these values in the lab report, and I will attach a photo for the tables with the data with this video.